So I talked about the JavaScript engine in the last lecture. But what is that engine actually? And what is a JavaScript runtime? Also, how is JavaScript code translated to machine code? So that's just some of the topics that we talked about in the last video. And so now let's find out how they work in this lecture. So a JavaScript engine is simply a computer program that executes JavaScript code. There are a lot of steps involved in doing that, but essentially executing JavaScript code is what an engine does. Now, every browser has its own JavaScript engine, but probably the most well-known engine is Google's V8. The V8 engine powers Google Chrome, but also Node.js, which is that JavaScript runtime that we talked about in the beginning of the course. So the one that we can use to build server-side applications with JavaScript, so outside of any browser. And of course, all the other browsers have their own JavaScript engines, which you can look up online if you're interested. Anyway, it's quite easy to understand what an engine is. But what's most important is to actually understand its components and how it works. So any JavaScript engine always contains a call stack and a heap. The call stack is where our code is actually executed using something called execution contexts. Then the heap is an unstructured memory pool which stores all the objects that our application needs. All right, so with this look at the engine, we have answered where our code is executed. But now the question is how the code is compiled to machine code so that it actually can be executed afterwards. Well, let's find out. But first, we need to make a quick computer science side note here and talk about the difference between compilation and interpretation. So in the last lecture, we learned that the computer's processor only understands zeros and ones, and that therefore every single computer program ultimately needs to be converted into this machine code. And this can happen using compilation or interpretation. So in compilation, the entire source code is converted into machine code at once. And this machine code is then written into a portable file that can be executed on any computer. So we have two different steps here. First, the machine code is built, and then it is executed in the CPU, so in the processor. And the execution can happen way after the compilation, of course. For example, any application that you're using on your computer right now has been compiled before, and you are now executing it way after its compilation. Now, on the other hand, in interpretation, there is an interpreter which runs through the source code and executes it line by line. So here we do not have the same two steps as before. Instead, the code is read and executed all at the same time. Of course, the source code still needs to be converted into machine code, but it simply happens right before it's executed and not ahead of time. Now, JavaScript used to be a purely interpreted language, but the problem with interpreted languages is that they are much slower than compiled languages. This used to be okay for JavaScript, but now with modern JavaScript and fully fledged web applications that we build and use today, low performance is no longer acceptable. Just imagine you were using Google Maps in your browser and you were dragging the map, and each time you dragged, it would take 1 second for it to move. That would be completely unacceptable, right? Now, many people still think that JavaScript is an interpreted language, but that's not really true anymore. So instead of simple interpretation, modern JavaScript engine now use a mix between compilation and interpretation, which is called just-in-time compilation. This approach basically compiles the entire code into machine code at once and then executes it right away. So we still have the two steps of regular ahead of time compilation, but there is no portable file to execute, and the execution happens immediately after compilation. And this is perfect for JavaScript, as it's really a lot faster than just executing code line by line. Now, I skimmed over some details here, but this is really all you need to know. Anyway, let's now understand how this works in the particular case of JavaScript. So, as a piece of JavaScript code enters the engine, the first step is to parse the code, which essentially means to read the code. During the parsing process, the code is parsed into a data structure called the abstract syntax tree, or AST. This works by first splitting up each line of code into pieces that are meaningful to the language, like the const or function keywords, and then saving all these pieces into the tree in a structured way. This step also checks if there are any syntax errors, and the resulting tree will later be used to generate the machine code. Now let's say we have a very simple program. All it does is to declare a variable like this. And this is what the AST for just this one line of code looks like. So we have a variable declaration, which should be a constant with the name x and the value of 23. And besides that, there is a lot of other stuff here, as you can see. So just imagine what it would look like for a large, real application. And of course, you don't need to know what an AST looks like. This is just for curiosity, okay? Now, sometimes I get asked if this tree has anything to do with the DOM tree, and the answer is a very clear no. So, this tree has absolutely nothing to do with the DOM. It is not related in any way. It's just a representation of our entire code inside the engine. Anyway, the next step is compilation, which takes the generated AST and compiles it into machine code, just as we learned in the previous slide. This machine code then gets executed right away, because remember, modern JavaScript engine use just-in-time compilation. And remember, execution happens in the JavaScript engine's call stack. But we will dig deeper into this in the next lecture. Alright, so far so good. We have our code running, so we can finish here, right? Well, not so fast, because modern JavaScript engines actually have some pretty clever optimization strategies. What they do is to create a very unoptimized version of machine code in the beginning, just so that it can start executing as fast as possible. Then, in the background, this code is being optimized and recompiled during the already running program execution. And this can be done multiple times. And after each optimization, the unoptimized code is simply swapped for the new, more optimized code without ever stopping execution, of course. And this process is what makes modern engines, such as V8, so fast. And all this parsing, compilation, and optimization happens in some special threads inside the engine that we cannot access from our code. So completely separate from the main thread that is basically running in the call stack, executing our own code. Now, different engines implement this in slightly different ways, but in a nutshell, this is what modern just-in-time compilation looks like for JavaScript. And the next time someone tells you JavaScript is an interpreted language, you just show them this slide so that they can learn how it really works. Alright, so we looked at the JavaScript engine and how it works behind the scenes in quite some detail. Now, to round off this lecture, let's also take a look at what a JavaScript runtime is, and in particular, the most common one, which is the browser. And by doing this, we can get the bigger picture of how all the pieces fit together when we use JavaScript. And so this is a really important slide. So, we can imagine a JavaScript runtime as a big box or a big container which includes all the things that we need in order to use JavaScript, in this case, in the browser. And the heart of any JavaScript runtime is always a JavaScript engine. So exactly the one we've been talking about. That's why it makes sense to talk about engines and runtimes together. Without an engine, there is no runtime and there is no JavaScript at all. However, the engine alone is not enough. In order to work properly, we also need access to the web APIs. And we talked about web APIs before, remember? So that's everything related to the DOM, or timers, or even the console.log that we use all the time. So essentially, web APIs are functionalities provided to the engine, but which are actually not part of the JavaScript language itself. JavaScript simply gets access to these APIs through the global window object. But it still makes sense that the web APIs are also part of the runtime. Because, again, a runtime is just like a box that contains all the JavaScript-related stuff that we need. Next, a typical JavaScript runtime also includes a so-called callback queue. This is a data structure that contains all the callback functions that are ready to be executed. For example, we attach event handler functions to DOM elements, like a button, to react to certain events, right? And these event handler functions are also called callback functions, okay? So as the event happens, for example, a click, the callback function will be called. And here is how that actually works behind the scenes. So the first thing that actually happens after the event is that the callback function is put into the callback queue. Then, when the call stack is empty, the callback function is passed to the stack so that it can be executed. And this happens by something called the event loop. So basically, the event loop takes callback functions from the callback queue and puts them in the call stack so that they can be executed. And remember how I said in the last lecture that the event loop is how JavaScript's non-blocking concurrency model is implemented? Well, here is an overview of how that works. Now, we will go over why this makes JavaScript non-blocking in a special lecture about the event loop later in the course, because this is really a fundamental piece of JavaScript development that every developer needs to understand deeply. All right, so as I already said, the focus in this course is on JavaScript in the browser, and that's why we analyzed the browser JavaScript runtime. However, it's also important to remember that JavaScript can exist outside of browsers, for example in Node.js. And so here is what the Node.js JavaScript runtime looks like. It's pretty similar, but since we don't have a browser, of course we can't have the web APIs, because it's the browser who provides these. Instead, we have multiple C++ bindings and a so-called thread pool. Now, details don't matter here at all. I just want you to know that different JavaScript runtimes do exist. All right, cool. That's all I had to tell you about JavaScript engines and runtimes. In the next lecture, we will learn how JavaScript is executed in the call stack.